In 2009, the Sayano-Shukhinskaya power station in Russia failed. This presentation is given by Colin Anderson, Kaylin Potter, Jansen Van Schaar, and myself, Nakai Sosi. The purpose of this presentation is to show how we would design a PID controller that would manage the input, which is a water flow rate, and how we would adjust and adapt to our desired output, which is energy production. The reason why this is so important is because if the power output is not within certain bands, vibrations occur and cause major wear and tear on the machinery. And in this specific case, it caused the entire power station to fail and explode. The power station operates between the bands of 0 and 350 megawatts and 550 megawatts to 650 megawatts. If it is outside these bands, that is what causes the vibrations to occur. The input flow rate also changes depending on the height of the water behind the dam, which changes throughout the year.
We are modeling a turbine power generation system where we have a dam and a gate, which is controlled by a valve, and this allows water to flow in through the penstock and down to the turbine where the power is being generated. Now we have certain ranges of power generation that need to be met because otherwise the generator vibrates too much, which is a safety concern. So the first step to controlling this process is to lay out the fundamental equations. First, we have our equation for flow, which is Q, and this is a function of the area of the gate that water is allowed to flow through, and this term, which is derived from the fact that hydropressure is being converted to kinetic energy. Once we have our flow, we can then plug it into this equation for power output, where eta is our turbine efficiency, rho is our water density, g is our gravitational acceleration constant, a is the area of the gate, as previously mentioned, h is the height of the water in the dam, and delta z is the height of the gate, or the gate position. Once we have these equations, we can plug them into our Python code with these two functions, flow rate and power output. And then later we're able to develop the code that's able to control this process as the height of the water in the dam changes throughout the year.
We needed to better understand our relationship between our inputs and our outputs. Our initial mathematical modeling treated the gate height of the inlet valve as our input and used that to calculate what the turbine power output would be. However, the turbine power output will be our process variable and will be our set point. It'll be set to either a high value or a low value, with anything in the middle being the danger zone. What this means is if we treat the gate height as the input, then the gain of our system will be different depending upon the set point. To remedy this, we swapped the input and output, treating the power output as our input to our controller, and treating the height of the inlet gate as our controller output. Using the depth of the reservoir as a disturbance variable, we simulated changes in power output by changing the depth of the reservoir, and used that to generate a model that allowed us to see the relationship between the power output and the gate height of the inlet valve.
Now we're on part 3 of our project where we create the PID controller. We take the values from our FOPDT model, plug them into the IMC moderate tuning correlations to obtain these values, and that gives us this untuned controller. We want to reduce a lot, especially these intermediate points, to reduce vibration on our system and possibly reduce the beginning and end point, weeks there. When we do that, we reduce our gain by 25%, remove most of those intermediate points so we have a nice long period of continuous automated operation. We still have the weeks at the beginning and end, which, as we see, there's 10 turbines in the whole plant anyway. They occasionally need to be maintained and shut down. That makes sense because in our starting week, people can just manually adjust the gate so that it can get up to where they can activate the controller. Same with at the end of the year when the dam level gets low, so that they just adjust it before reactivating the controller.
And in conclusion, we were able to design and code a PID controller that managed the valve that controls the input flow. Some of the assumptions we made were that water properties were constant, that all the energy from the dam comes from potential energy, that there was no pressure loss throughout the entire system, except for at the turbine, And we also recommend that in order to avoid the problem that caused the destruction of the dam, that you manually open the valve when it's going from the high bands of operation to the low bands of operation, so that you don't have days of where the valve is opening and closing. And that concludes our presentation. Thank you so very much.